we did change of basis. Sorry, we did bases and dimensions, and I wanted to go over change of basis. Before I start this lecture, a few updates. IBA has been completely closed down, which means even faculty members don't have access to the offices, and so I can't record these videos in the office, which means I no longer have a noise-free environment. I live in a very noisy neighborhood. So if the audio is not great, I apologize for that, but there's really nothing I can do about it. I will try. I've tried to do as much noise cancellation as possible, but yeah. Anyway, so let's hopefully focus on the lecture and get through this. I'm not sure how the semester is going to play out. I'm not sure how the exams and midterms, all of that is going to play out at this point. I have as much information as you do, and honestly I'm also questioning the point of doing all of this, but I think there is one thing that perhaps we can all agree on. I don't want to waste this time. We have, I don't know how many holidays in front of us. This could extend to May, this could go beyond May. So instead of sitting idly and doing nothing, let's just, learn something, and let's just fulfill at least some of the basic goals of the course. So let's do that, and perhaps, I don't know, maybe let's be a bit optimistic. We might be even able to do some form of assessment, examination, blah blah blah. Anyway, enough of my rambling on the screen. Let's get to the idea. So the idea is we did bases and dimensions, and we said that if you have a vector space and you can express the basis vectors can be different. So for example, if I move to this view, so for example, if you have a vector space V, you can have different bases for this vector. We already know there are some standard bases, but perhaps you can have another basis for this, perhaps a collection. Let's suppose we're talking about R3. So the standard basis in R3 is just E1, E2, and E3. But of course you can have other sets of vectors as well. This was the standard basis. Another basis could be, I don't know, perhaps let's say V1, V2, V3. And recall that to be a basis, it needs to satisfy two criteria. The first criteria it needs to satisfy is that VI's, this should be linearly independent. That's the first criteria. And the second criteria is, of course, that VI's should span R3 or whatever vector space you have at your disposal. If this collection of vectors satisfies these two conditions, then we know that this collection is a basis for R3. And so the question is, if, let's suppose I have a vector space and I have several different bases for it. Let's suppose I have a collection V1, V2, V3, U1, U2, U3, and E1, E2, E3. All of these, I'm assuming, forms a basis for my vector space. So if I take any vector x, I know that if V is a basis, then I can express x and represent it as a linear combination of the vectors in V, or the vectors in U, or the vectors in E. So I can express x as a linear combination of E1, E2, and E3. And so I just need some scalars, x1, x2, and x3, and this is a linear combination, and x is equals to this, where x1, x2, and x3 can be called the coordinates of x with respect to this basis, E1, E2, E3. And this is simple. If you recall your R2, then or R3, then this is just the basic coordinates, the Euclidean coordinates rather, that you deal with. But that's not the end of the story. You can of course express x as a linear combination of V1, V2, and V3. But of course now the scalars will change depending on what V1 is, what V2 is, and V3 is. We will have to use different scalars, and then these alphas, alpha 1, alpha 2, alpha 3, will be the coordinates of x but now with respect to a different basis. Same is the case for, I seem to have written v1s again. One of them is supposed to be u1, u2, u3, so that's a typo here. You can fix that at your end. Anyway, and so the basic question that we now have to deal with is, how do I switch between these different bases? How do I go from x1s to alpha 1s? Or if I have alpha 1s, how do I find x size? How do I switch representations of matrix X between different of the vector X between these different bases? If I have these coordinates, how do I find these coordinates? If I have these coordinates, how do I find these coordinates?
The Google Assistant has been disabled by your account administrator. To continue, please.
Okay, sorry about that interruption. So as I was saying, the question is, how do we switch between different coordinate bases? How do I find alphas if I have betas? How do I find betas if I have alphas, and so on and so forth? The applicative question of why do I need to switch between coordinate bases? Well, there are different applications where we need to work with different bases. In some applications, specific coordinate bases are easier to work with rather than the standard bases. If you want to find out the applications of switching between coordinate bases, you can Google that on your own. I'm not going to spend time on that question. Okay, so let's consider a 2D case. Let's suppose I have 3 collections which are bases for a 2-dimensional vector space. I have, of course, my standard basis, which is E1 and E2. And let's suppose I have another basis U1, U2 and V1, V2. The question is, let's consider these 2 bases first. How do I switch between the standard basis to this basis and from this basis back to the standard basis? If I can solve this problem, then you could think and you can convince yourself that that's the only 2 problems that I need to solve, because if I want to go from this basis directly to another basis, then all I can do is figure out how to go from this basis to this basis and then go from this basis to this basis. So if we can figure out how to go from a standard basis to a non-standard basis, then I can go from one non-standard basis to another non-standard basis. So I repeat, the idea is, if you want to go from one non-standard basis to another non-standard basis, all you need to figure out is how to go from a non-standard basis to the standard basis, and from a standard basis back to a non-standard basis. If we can figure these 2 components of this problem, then this entire problem is easy to solve. So let's look at the easier problem first. The easy problem is, how do we go from this basis U1, U2 to the standard basis E1 and E2? Let's suppose I have U1 as 3, 2 and U2 as 1, 1. These are 2 linearly independent vectors. You can check that they're linearly independent. And now let's assume I have a vector x which is written as a representation in this basis. So x is represented as C1 U1 plus C2 U2. And let's do this process on our own. Let's figure out how we'll do this. So I repeat, we had x as C1 U1 plus C2 U2, and let's just write down what U1 was. U1 was 3, 2, and so U1 I have as 3, 2, and U2 I have as 1, 1. So now the idea is as follows. This is the representation of x in terms of these 2 vectors U1 and U2. How do I move? How do I figure out, how do I find the representation of x in terms of E1 and E2? First, think about these vectors U1 and U2. Notice that I can write U1. U1 is just another vector in R2. Even though it's a basis vector, it's still just a vector in R2, which means you can just write U1 in terms of the standard basis. If I just write it as 3e1 plus 2e2, then I'm representing my basis vector in terms of the standard basis. Similarly, I can write U2 as 1e1 plus 1e2. So I've done nothing but represent these two basis vectors in terms of the standard basis. Okay. Now consider this. X was simply C1 U1 plus C2 U2. I have already expressed U1 in terms of E1 and E2 and U2 in terms of E1 and E2. Then I can expand this expression and write C1 3E1 plus 2E2 plus C2, these are vectors, 1E1 plus 1E2. I can collect the terms in E1, which will get me 3C1 plus C2 E1 plus 2C1 plus C2 E2. And you can see now that X has been represented in terms of the basis vectors E1 and E2. So I can just write X now as X1 E1 plus X2 E2, where I have X1 as 3C1 plus C2 and X2 as 2C1 plus C2. That's my X1 and X2, where X1 and X2 are the coordinates of X in terms of the standard basis. Okay, but how does this tell me how to go from these coordinates to these coordinates in a general setting? Let's make this a bit more convenient for us. Let's write this again and express it like this. I can write this as 3, 1 and 2, 1, where this is C1, C2 and this is just C1 and C2, where this was just simply the vector x1 and x2. So I'm writing this as this. Now we can express this. If I write this down as a matrix vector multiplication, let me separate the coefficients and separate the vector C1, C2 from this. Note that when you multiply these two, 3C1, when you multiply this matrix with this vector, you get 3C1 plus C2 and 2C1 plus C2. Then this is just, now this on the left hand side you have x1, x2, the coordinates for the standard basis. These are the coordinates for the bases U1 and U2. And this matrix, if you notice closely, this matrix is nothing but, if I call this matrix U, then this matrix is nothing but the first column is made up of vector U1 and the second column is made up of the vector U2, where U1 and U2 were the basis vectors that I was trying to switch from. This is U1, this is U2. So let's see what we have on our hands. I have expressed x1, x2 is equals to 3, 2, 1, 1, C1, C2. If I write this as x, if I call this matrix U, capital U times C, then this equation gives me a way to switch from these coordinate vectors, this coordinate vector C, to the coordinate vector x. And this matrix we call the transition matrix. So the first part is done. The first part, which was that if I have for the collection U1, U2, if I had coordinates C1 and C2 such that x was equals to C1 U1 plus C2 U2, then I have a way to switch from C1 C2 to x1 x2, where x is simply x1 E1 plus x2 E2. And the way to do that is simply multiply C with the transition matrix U, and you will get the coordinates in the standard basis, which is a very simple thing to do. Question at this point is, if I have found a way to go from U1 U2 to E1 E2, if I have found this way, how do I find the other way around, which is, how can I now write C equals to some matrix times x? And that problem is easy to solve. You already have this equation. If I multiply the equation x equals to uc with the inverse of u on both sides, I get c equals u inverse x. And the question is, does the inverse of u exist? If you recall, the inverse of a matrix exists if the matrix is non-singular, and there was another equivalent condition that we learned, that a matrix is non-singular if the columns are linearly independent. Matrix U was nothing but, matrix U was made up of U1 and U2 as its columns. Are the columns of U linearly independent? Well, of course they are, because we claimed right at the start, we assumed that U1 and U2 was a basis. And basis, we know that the collection of vectors that makes a basis has to be linearly independent. So we are guaranteed that these two vectors are linearly independent, and hence this matrix is also invertible, and the inverse of this matrix exists, which is U inverse. And so you have a way to now go from coordinates C1, C2 to X1, X2 and X1, X2 to C1, C2. All you need to find is matrix U. You had this non-standard basis. So if I can write it down in terms of steps, if I want to go from the standard basis E1, E2 to back and forth from U1, U2, all you need to do is write down the transition matrix by taking the non-standard basis as columns. And you immediately have x is equals to uc and c is equals to u inverse x. These are the equations which will translate c to x and x to c. Okay, moving on. Now, of course, as an example, I showed you just a two-dimensional case. This was the case we did for 3, 2, and 1, 1. And we converted them from x to c and c to x. And so, of course, I just showed you a two-dimensional case, but nothing is stopping us from expanding this case to 3 dimensions, 4 dimensions, n dimensions, right? And the idea is the same, that you make an n-dimensional transition matrix using the vectors of your non-standard basis, and you have it. Okay, so now let's address the remaining problem. The remaining problem was, how do I go from one non-standard basis to another non-standard basis? And this can be done as follows. Let's suppose you have a route from a non-standard basis to x1, x2. That is the standard basis. And you have the route from another non-standard basis v1, v2 to e1, e2, which was using this transition matrix V. So I can write down from here to here, I can write down this equation, x is equals to uc, where u is a matrix made up of the columns as these vectors, And if I have to go from V1, V2 to E1, E2, I can write down a similar equation, x is equals to Vt. And now I can just get rid of x from this picture and just deal with, if x is uc and x is vd, I can write uc equals vd, and now take this, multiply with the inverse of u on both sides, I get an identity here, and on the right hand side I get u inverse vd. So this is now a route to go from the coordinates d to coordinates c. The coordinates d were the coordinates of matrix of vector x under v1 and v2, and coordinates c were the coordinates of x under u1 and u2. And now this equation will give you the route from v1, v2 to u1, u2. You could have done it the other way around as well. Multiply it with the inverse of v on both sides and you get d equals to v inverse uc. And so now you can move from one non-standard basis to another non-standard basis, right? Okay.